Hi guys, in this video we will be dealing with the qualitative analysis test for anions. We've got a number of anions that we need to test for in the lab, and these anions have individual tests that we need to remember. So these anions include the carbonate ion, the chloride ion, the bromide ion, the iodide ion, the nitrate ion, the sulfate ion, and the sulfite ion. So let us begin with testing for anions. We will start test for anions with the halide ions. So the halide ions in our syllabus are chloride, bromide, and iodide. They each have the same test being performed but with different results. So for chloride ions, we add silver nitrate aqueous followed by nitric acid. Or we can do this in the opposite order. First, we add nitric acid followed by silver nitrate. So the observation that we will obtain with silver nitrate is a white precipitate forms, and this white precipitate will be of silver chloride, because if we have Ag positive ions being introduced into our solution in which Cl negative ions are already present, they will form an insoluble precipitate of AgCl, which is white in color. So this white precipitate is of silver chloride. Now, when we add excess of dilute ammonia in this silver chloride, this silver chloride dissolves to form a soluble complex, and we are left with a colorless solution. So this out of the three halide ions is the only one that would dissolve on addition of dilute aqueous ammonia in excess. Bromide and iodide ions will not give a colorless solution when dilute aqueous ammonia is added to it. So the white color distinguishes chloride ions from bromide and iodide ions. With bromide ions, we will be again adding silver nitrate followed by nitric acid, or nitric acid followed by silver nitrate. Either of the two methods are okay. So the observation here would be a cream precipitate forms, which is soluble on addition of excess concentrated ammonia, and insoluble on addition of excess dilute ammonia. Now, the thing is, it is soluble on addition of excess concentrated ammonia. Now, concentrated ammonia is how we receive ammonia from the chemical industry, and we will not be doing this test in the lab because concentrated ammonia is dangerous. So, we are only left with dilute ammonia in the lab, and this precipitate does not dissolve with dilute ammonia. So, the precipitate would remain on addition of dilute aqueous NH3. Now, the color. We have a white color for chromium. Oh, sorry, chloride, not chloride. We have a white color for chloride, and we have a cream color for bromide. Now, these colors are different. When the color appears, you will see the white color as bright white. But for bromide ion, you will have an off-white or a slightly pale brown precipitate forming that can be called as the cream color. So I'll try to show the difference between these two colors here. This is how a white color would appear. Look at the white color that I am shading on the black box. This is the appearance of a white precipitate, this white color. However, if we have a cream color, I'm just going to put it next to this one. If you look, there is a difference in color. Now, this difference in color is hard to notice, but if you get used to it, it will become easier. This is the color of the AgBr precipitate. So now let's put the two colors together. Here I have white at the top, and here I have the cream color at its bottom, and I've combined the two colors to show you that yes, there is a difference between them. So as you can see, the one at the top is of chloride ions, and the one at the bottom is for bromide ions. So these are the color changes when you add silver nitrate to chloride and bromide ions. Continuing on with the test for halide ions, the next ion we have is iodide. And when we add silver nitrate followed by nitric acid or nitric acid followed by silver nitrate, we end up with a yellow precipitate. So here you can see the yellow color that you will get, and this color is very much different from the cream or the white color that you obtained for silver chloride or silver bromide. So this is the color for silver iodide. So now let's compare the three colors. This is the color for iodide ions. This is the color for bromide ions, as you can see here. This is the precipitate for silver bromide that you will obtain. And for silver chloride, it is white. So here, clearly you can distinguish between the three colors of the precipitates, and I've shaded these as close to as the original colors that you obtain in your tests, right? So let's label these. The first one, the yellow color is iodide ions, the cream color is bromide ions, and the white color is for chloride ions. In fact, the yellow color is for silver iodide, the cream color is for silver bromide, and the white color is for silver chloride. So hopefully the colors make it easier to remember. Okay, so the observation here states a yellow precipitate forms which is insoluble on addition of excess dilute or concentrated ammonia. Here, even if you add concentrated ammonia, it will not dissolve. So this precipitate remains insoluble where in ammonia, whichever concentration of ammonia you use. So these were the tests for the halide ions. Continuing on with the test for anions, the next anion that we are testing for is carbonate. Now, the formula of the carbonate ion is CO3 with a charge of -2. And the test for carbonate ions is the same test that we perform for acids. When we add an acid into a solution or a solid containing carbonate ions, we would end up with effervescence. Effervescence is basically bubbling observed in the solution, right? Now, since we are adding acid into a solution of carbonate, we would see bubbling in the solution. And if we add solid carbonate into a solution of an acid, again, we are going to see bubbling, but this bubbling would be uh, having a white colored salt and the bubbles mixed together because the carbonate is solid in the second example. So for references, let's use a solution of sodium carbonate and we add dilute HCl to it. So you can see bubbling occurring within the liquid itself, and it's colorless liquid. So colorless liquid has bubbles evolving. Now, this evolution of gas is known as effervescence, the bubbling. Effervescence and a colorless gas evolves, and this colorless gas is carbon dioxide. So when this evolves, we pass this using a delivery tube into a test tube containing lime water. Now, what is lime water? Lime water is calcium hydroxide aqueous. Calcium hydroxide, when placed in water, dissolves partially, and then when we filter it, we are left with lime water. Now, this lime water, upon reaction with carbonate ions, results in the formation of calcium carbonate. Now, calcium carbonate is an insoluble salt and it is white in color. And we are left with two hydroxide ions that were released by calcium hydroxide. So, the calcium hydroxide aqueous solution was colorless. Upon addition of carbonate in the solution, we end up with a white precipitate forming, to which we refer to as lime water turns milky. The milky color is due to the formation of calcium carbonate and the presence of calcium carbonate in the solution. So this is the test for carbonate ions. Usually when the test is actually performed, because of effervescence upon addition of an acid, we will state that effervescence and a colorless gas evolves, which turns lime water milky. But in most cases, we do not perform the test for lime water turning milky because upon addition of acid, effervescence and a colorless gas evolves always indicates the presence of carbonate ions. The next ion we'll be testing for is the nitrate ion. Nitrate ion has a formula of NO3 minus, and if nitrate ions are present in our solution, when we add dilute NaOH, we follow it up by addition of aluminum foil and heating it. When we add these three reagents into our solution containing nitrate ions, as in two reagents, and then we heat it. So the observation is an effervescence, that means bubbling will be seen, but this bubbling is because of the reaction along with it being heated, right? And a colorless gas evolves. Now this colorless gas is ammonia. So this reaction produces ammonia. So ammonia gas is evolved, and when ammonia gas is evolved, it turns a damp red litmus blue. Okay, how does this happen? Litmus paper has a red colored appearance in acids and a blue colored appearance in bases, which is the appearance of the litmus indicator itself. So litmus indicator is coated onto the paper. In order for litmus to change color, the ammonia being produced must be present exposed to the litmus. So we dampen the litmus by pouring distilled water over it, right? So it becomes wet. And when the gas is released from a tube, this gas dissolves in the water present on the litmus paper, converting into aqueous ammonia. And this aqueous ammonia changes the color of the litmus paper from red to blue. So this is a clear indication of the presence of nitrate ions. The next ion we will be testing for is sulfate. Sulfate has a formula of SO4 with a 2 negative charge, and there are two ways of testing for sulfate. One is written here, add barium chloride followed by HCl. We need to keep the anion the same. So in this case, if we have the chloride ion, then we add HCl. Or another test can be performed in which we can add barium nitrate. And since the anion in this reagent is nitrate, we will follow it up by the addition of HNO3 aqueous, nitric acid. So there are two ways of testing for sulfates, which is barium chloride followed by HCl or barium nitrate followed by nitric acid. Both of them will give the same result. What is the observation? A white precipitate of barium sulfate will form. Yes, which does not dissolve on addition of HCl. Okay, now we need to understand why HCl is added later and not in the beginning. If instead of sulfates, sulfite ions were present, sulfite ions have the formula SO3 2 minus, and we will be looking at sulfite ions shortly. Sulfite ions, upon addition of a white precipitate of barium sulfite, will dissolve upon addition of excess acid, whether it be HCl or HNO3. So barium sulfide is soluble in acids, whereas barium sulfate is insoluble in acids. So we will introduce barium ions first, followed by the acid, so that we can distinguish between the presence of either sulfate or sulfide. Our next ion is sulfite ion. Now this sulfite ion has a similar test to sulfate ions, which is we add barium chloride followed by HCl, or we add barium nitrate followed by HNO3. Whichever test we perform, we end up with a white precipitate forming when barium ions are introduced, but this white precipitate dissolves to form a colorless solution upon addition of the acid in excess, whether it be HCl if BaCl2 is added, or it is HNO3 when BaNO3 twice is added. So this is how you differentiate between sulfate and sulfite ions. Sulfate ions will form a white precipitate which will not dissolve. Sulfite ions will produce a white precipitate which will dissolve. And we can do one more test. On heating, a colorless gas, which is SO2 in this case, evolves, which turns acidified potassium manganate from purple to colorless. Okay, so on heating, a colorless gas evolves. So we are testing for gas. So we need a delivery tube to transfer the gas into a test tube containing acidified potassium manganate. That is one way of testing it. Another way is we dip a filter paper in acidified potassium manganate and place this paper over the test tube so that when SO2 gas evolves, it is absorbed into the potassium manganate paper and the color fades, as in it goes from purple to colorless. Or there is another way. When we add the acid in the test tube containing sulfide ions and barium ions. So the precipitate will dissolve. When in this test tube, if you add potassium manganate solution directly, a few drops, you will observe that they will convert into a colorless, as in the color will change from purple to colorless. And whenever potassium magnet has a color change from purple to colorless, it means it undergoes reduction, and as an oxidizing agent, it has oxidized whatever is present in that solution. So now we had sulfide ions present. So potassium magnet converted sulfide ions into sulfate ions. This can be tested further. Now again in this very same test tube, if you add barium chloride or barium nitrate, a white precipitate will form. And now when you add HCl or HNO3, this white precipitate will not dissolve, indicating the presence of sulfate, which was not there in the beginning. This means that potassium manganate converted the sulfide into sulfate by oxidizing it. And when we added the barium chloride for the second time, we now had a precipitate of barium sulfate instead of barium sulfide forming. That is why it did not dissolve in the acid that was added after it.